Hey guys, it's Mrs. Kraus, and this video is going to teach you how to do the statistics that you'll need to do for the cell signaling statistics assignment. What I'd like you to do first is please read this paragraph of information next to the pufferfish image. You can pause the video to do so. Okay. Now that we're back, after that paragraph of information, it says, let's say scientists wanted to design an experiment to see if applying TTX to nerve cells would affect the amount of sodium ions entering the nerve cell. They compared the TTX nerve cells to normal nerve cells that were not exposed to TTX. The first question you're asked is, what is the null hypothesis for the experiment? And the null hypothesis is something that we talked about a long time ago when we did chi-square test for our earthworm behavior lab. And our null hypothesis then was there's no statistically significant difference between the number of earthworms on the light versus dark side of the box. All null hypotheses start like that. There is no statistically significant difference between two things. In this case, our null hypothesis would be there's no statistically significant difference between the number of sodium ions entering the TTX nerve cells versus the normal nerve cells. You can pause the video if you need time to write that down. If we define a null hypothesis, we also want to define an alternate hypothesis. So if the null hypothesis is not true. So we can express our alternate hypothesis using two methods, method A and method B. With method A, we just have the exact opposite statement of the null hypothesis. Instead of saying there is no statistically significant difference, we say there is a statistically significant difference between the number of sodium ions entering TTX nerve cells versus normal nerve cells. Method B is putting that alternate hypothesis in if-then format and actually making a prediction for the experiment. So here we have if nerve cells are exposed to TTX, then fewer sodium ions will enter these TTX nerve cells than normal nerve cells. So you can pause the video if you need to write this down. Okay. All right, now after we write down the null and alternate hypotheses, they show the actual data for the experiment, where they conducted 5 trials, and during each trial they counted the number of sodium ions entering the TTX nerve cells versus the number entering normal nerve cells. They've also given us a sum total across the 5 trials of the number of sodium ions entering each type of nerve cell, and then the total number of sodium ions in the experiment as a whole. Okay. We're going to do some statistical calculations to compare the two data sets, the TTX versus the normal nerve cells, starting with mean. Now, the mean formula that's given on the AP Bio formula sheet is also given here at the bottom of the page, and the formula is extremely confusing, but hopefully at this point you know how to calculate mean. We calculate the mean by adding our values together and dividing by the number of values. That gives us an average. So that brings us to our next calculation that we're going to do, which is called standard deviation. We use standard deviation to figure out the amount by which each data point typically differs from the mean. It basically tells us how much variation we have in our data set, so how our data points are spread out around the mean. This is the formula that's given on the AP Bio formula sheet, and you're also given some information about the terms in that formula. For example, X with a bar over it, they tell us that that's the sample mean. I just like to think of it as the mean. N is supposed to represent the size of the sample. I like to think of that as the number of data points. And then S is the standard deviation, and they give us a bunch of other mumbo jumbo, but it's just the standard deviation. Okay. Other terms that they don't give you information about in the AP Bio formula sheet would be X with a little I, that's each individual data point, and a sigma symbol, which stands for sum. So what we're supposed to do with the standard deviation formula is we want to take each individual data point and subtract X bar, which is the mean. We then square that, We do that for each individual data point. We write them all down and we add them all together. We then divide that sum by n minus 1 and we take the square root of the whole thing. So let me give you an example. Let's say my data set had 5 values in it, 2, 4, 6, 8, and 10. To find the mean, or x bar, I would add them all together and divide by 5, since there are 5 data points. That gives me a mean of 6. When I'm calculating my standard deviation, I start by taking my first data point, 2, that's xi. I subtract 6, my mean, which is x bar, and then square it. I then add that to my next data point, 4 minus 6, my mean, square that. I add it to my next data point, 6 minus my mean, 6 squared, and so on and so forth until I've done it for all of my data points. I then divide that sum by n, which is the number of data points, 5 minus 1, and I'm going to divide that ultimately by, I'm going to take the square root of the number that I get. So I end up with a square root of 10, which is 3.16 for this example data set. All right, now I want you to go ahead and do that calculation now. I want you to calculate the mean for the TTX nerve cell data and the mean for the normal nerve cell data. And then I also want you to calculate their standard deviations and show your work. Okay, so go ahead and pause the video now until you've had some time to do that. Okay, so let's see. I ended up with 7 for my mean if I'm rounding to the nearest whole number for the TTX nerve cells, and 66 is my mean for the normal nerve cells. When I did my standard deviation calculation, I ended up with 3.54 for my TTX nerve cells and 5.36 for my normal nerve cells if I'm rounding to the nearest hundredth. Okay. Next thing we're going to be calculating is called the standard error. We use the standard error to figure out how precise the mean value is. And we do that based on 2 things, the standard deviation, which is S, and then the number of data points, which is N. So the way that we calculate this is we take S, the standard deviation, and we divide it by the square root of N, the number of data points. And that gives us the SE x bar, or sometimes they write it as SEM for standard error of the mean. Now we're confident in the precision of our mean if the standard error is low. This happens when S, the variation, the standard deviation, is low, and also the sample size is high. So that means all of our data points are close to the mean, and we also have a lot of data points, so we're pretty confident. Okay. Now, I have some suggestions. If you're using a baby calculator, you can calculate the square root of n and either write it down with all of its decimal points, or you can save it in your calculator using the m+ button. So then you type in s, and you divide it by the square root of n by either typing the value you wrote down for the square root of n or hitting the MRC button. And you can get rid of the value you saved by, I believe, hitting M-. So for this sample data set that we had used, 2, 4, 6, 8, and 10, remember we calculated our standard deviation was 3.16. So if I'm calculating standard error of that, I take 3.16 and divide by the square root of 5, since there were 5 data points, and that would give me 1.41 as my standard error. Okay, what I'd like you to do now is please go ahead and calculate the standard error of the mean for your TTX nerve cells and also your normal nerve cells. And go ahead and pause the video until you're done. Okay, I calculated my standard error of the mean for the TTX nerve cells to be 1.58 if I'm calculating to the nearest hundredth, and 2.40 for the normal nerve cells. Again, that's 1.58 for TTX and 2.40 for normal. All right. All right, And that brings us to our next calculation, which is the 95% confidence limit. Now, the 95% confidence limit says if we were to sample a larger amount of data, we're 95% confident that the real mean for that larger set of data would fall within a particular range. And that range is actually going to be the error bar when we make a graph of the mean. So we'll show you what error bars on graphs look like in just a minute. So we can calculate the 95% confidence limit by taking the mean value for your data set, and you can add 2 standard errors to get the upper part of the range, and you can subtract 2 standard errors to get the bottom of the range. So for example, let's say I was doing this for my sample data set where I had my values as 2, 4, 6, and 8. 6 was my mean, so I can find the error bar upper limit by taking 6 and adding 2 times my standard error, which was 1.41. So my error bar upper limit would be 8.82. My error bar lower limit would be 6 minus 2 standard errors, which would be 3.18. I could actually graph the mean value of 6 on either a bar graph or a scatter plot like I've shown here. So the top of the bar and the point on the scatter plot would be the mean, 6, and then my error bar upper and lower limits would be the top and the bottom of the error bar. Okay, so I would have 8.82 at the top and 3.18 at the bottom. Okay. Now let's say we were graphing 2 means with error bars. If we were graphing the means of 2 data sets and we saw that there was some overlap in the error bars, like we see this whole red region is an overlap between the error bars of these 2 means, that means there may not be a statistically significant difference between the 2 means. Now let's suppose we were graphing the means of 2 data sets and the error bars don't overlap, like this entire blue region is the space between the 2 error bars. There's no overlap. That means that we may have a statistically significant difference between the means. However, further statistical tests are needed to determine for sure. So let's say I'd like you to go ahead and find the error bar upper and lower limits for the TTX and the normal nerve cells. And then I'm going to have you graph the error bars for a bar graph. So you're going to have 2 bars, one for each mean, and you're going to have an error bar for each of your bars. Then you're going to decide if there's overlap between the error bars for the 2 data sets. Okay. And you can go ahead and pause the video until that's done. And when I did it, let's see, I found that the error bar upper limit for the TTX nerve cells was 10.16 and the lower limit was 3.84. The upper limit for the normal nerve cells was 70.80 and the lower limit was 61.20. Then, when I graphed them, I could very distinctly see that there was no overlap between the 2 error bars, and that means we may have a statistically significant difference between the 2 means. Okay, now we're going to do a chi-square test, which we've done before, so I'm going to run through the steps really quickly. We use a chi-square test to determine if we should reject or fail to reject, which means support our null hypothesis, which says there's no statistically significant difference between the 2 means for the TTX nerves and the normal nerve cells. Remember, we always state our null hypothesis. It's always a negative statement saying there's no statistically significant difference between. Next, we are going to find our expected values. So these are expected values based on the null hypothesis. We would do that by finding our expected decimal frequencies and multiplying by the total sample size to get whole numbers. So in our next video, we're going to start by doing that.